uniformly at random. For instance, you can assume you throw a fair coin, and if the coin gives you a head, you write a 0. If it gives you a tail, you write a 1. It doesn't really matter how you do it. The important thing is that you generate bit strings of length 4 at random. Now, what is the probability that a bit string contains at least 2 consecutive zeros, given that you know that the first bit is a 0? Okay, now the information that somebody gives you is that the first bit in the string that you've generated is a 0. You want to calculate, under this assumption, the probability that the bit string contains at least 2 zeros in a row. Okay, so let's try to do that using, okay, now we are in business because we can start calculating. And if we can use this formula to calculate what is the conditional probability that we get 2 zeros, at least 2 zeros in a row in our string, given that we know, somebody told us that the bit string starts with a 0. Okay, so what is the probability that the bit string of length 4 starts with a 0? It's a half. Okay, so the probability of f is a half. Now, this makes intuitive sense. Why? Because the first bit is determined by stuff in our formula. In fact, let's start plugging. So this is going to be 2 times the probability of E intersected with F. Why 2? Because the probability of F is a half, and it's under the fraction. Okay? Okay, so all we're left to do now is to calculate the probability of E intersection F. Now, what's that? Okay, this is the collection, the probability of a set of possible outcomes. And what is in this set? They are all of the bit strings of length 4 that start with a 0 and have at least 2 consecutive zeros somewhere. Okay, so let's see. What are they? Okay, so you start with a 0. If afterwards you see another 0, then it really doesn't matter what follows, because you've seen at least 2 consecutive zeros. So let me write xy here. For xy are just bits. Doesn't really matter what they are. Union what? Okay, so you have 0 followed by 1. Now, if your bit string is of length 4, it starts 0, 1, and it contains at least 2 consecutive zeros. I think you get a pretty good idea of what must follow 0, 1. It must end with 0, 0, because I cannot see 2 consecutive ones. Zeros. So that's the only other possibility. Okay, so if the string starts with 0, 0, then anything goes. If the string starts with 0, 1, that since you want to see 2 consecutive zeros and the bit string is of length 4, the string must continue with 0, 0. So how many strings are in this set? What is the cardinality of the intersection F? There are 5 of them, because there are 4 in the first set and only 1 in the other set of the union. There are 4 because you can choose x, y as you like. There are 4 possible bit strings of length 2. So that's 5. I think we now know what is the probability of E intersected F. What is it? Okay, there are 5 good guys How many? There are 16 possible bit strings of length 4. It's 2 to the power 4. Because at each position, you can choose, do I put a 0 or I put a 1? And I make this choice 4 times. If somebody tells you, okay, the string starts with a 0. This is higher than if somebody told you nothing. It tells you, well, here's an arbitrary bit string of length 4. What is the probability that you get 2 consecutive zeros? Well, that's actually lower. And you can compute what it is at your leisure. Okay, any doubt about this? Again, the numerical stuff, it's not important. What is important is the way we went about, which is, for instance, that's an event with very high probability that you will be working on test 2, and so you should. But since you're also supposed to work at home when you don't have anything better to do, here's some practice exercise for you. That's your gym. Okay, so in general, let's try to figure out how we go about solving this problem. And here's a checklist in case you really want to get it right, because you really want to get it right. Whenever you're dealing with a probability question, if you're not sure about the result, or even if you're so zeros, again, I keep flipping zeros and ones here. F was the collection of all bit strings that start, or length 4, that start with a 0. E intersection F, the collection of all of the bit strings that start with a 0 and have 2 consecutive 1s in them. Once you figured out what are the events of interest, you assign them probabilities, like we did before. And once you have the probabilities of the events of interest, you just shake them all together according to the cocktail that you want to make, and out comes the answer. And the recipe for the cocktail in our previous example was the formula for calculating the conditional probability of E given F. All we need to do was to plug in the probability for E intersection F and for F in that formula, and we got the answer. Okay, that's the checklist. So let's put it to work. Suppose that we want to figure out what is the conditional probability that the family with 3 children has 2 girls, given that they have at least 1. And of course, we assume that every time a child is born, it has a 50% probability of being a girl as well as a 50% probability of being a boy. That's not quite accurate. There are, I think, more women than men in general, and it's more likely that we get women, I believe, but it doesn't really matter. We are not pretending to be true to life. Okay, so let's follow the checklist. What is the sample space? What are the events of interest? What are their probabilities? And what is the answer to the problem? So let's see. So we want why? Well, one easy way of calculating this is to say which one is the only outcome. There's only one outcome, actually, that doesn't have at least 1 girl, and that you get boys all the time. So boy, boy, boy. Some people might find it boring. That's why B, 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 B. Well, no, I mean, so I don't know. It happens. My wife had three boys. That's why then she decided to adopt a girl. At some point, you just have to give up and say, okay, I'm going to get another boy. So if I try, so let's adopt a girl. Okay, so there you are. So there's only one that doesn't work. So the ones that work are 1 minus the probability of getting the bad BBB thing. That's 1/8, so it's 7 out of 8. So the probability of F, it's 7 out of 8. Okay, so let's look at another event of interest, which is exactly 2 girls. Okay, so what is the probability of getting exactly 2 girls? Well, let's spell it out. Okay, so you can get 2 girls to begin with, or you can get a girl, then a boy, and a girl, or you can start with a boy, and then you get 2 girls. I don't think there are any other possibilities. Okay, so what's the probability of getting exactly 2 girls? 3 out of 8. Okay, now it sounds like we want to do a conditional probability calculation, because the question was, what is the probability of getting exactly 2 girls if you have at least 1? Okay, in order to do so, we have a missing ingredient. Namely what? The intersection. Okay, so this is actually the same as E, isn't it? Because every family that has exactly 2 girls has at least 1. Okay, at least 1 is more generous. So for instance, you can have girl and then boy, boy, then you have at least 1, but you don't have exactly 2. Well, actually, that's not quite right. That's not quite right. You should never believe what I say. You should never believe what I say. Verse 7. Now, this makes perfect sense intuitively. Why? Because if somebody tells you you have at least 1 girl in the family, then your sample space shrinks. It was 8 strong before, it becomes 7 strong. The possibility boy, boy, boy has disappeared. But the good family combinations are still 3. They were 3 before, they remain 3, but now the probability is 3 out of 7, not 3 out of 8. Which was the probability that you would assign to the event exactly 2 girls before somebody told you, and by the way, the family has at least 1. Okay, so we revise our probability estimate based on information that we get. Say it again. Sorry, just.
So you have a string of 3 people.
Yes.
And you know one is a girl. But then to come that not and like exactly 1 girl in a string of 2. But it not be the same.
The question is, okay, so why doesn't it give me the same solution if I remove, so I know that in my string there is 1 girl, so I remove that and I want to find exactly 1 in the other 2. But there are 3 possible positions where the girl told you to do pedantically. Then you can start improvising, at least if you want to eat something the first time around. And if the recipe is complicated, then you better follow it. You just increase your chance of having something decent to eat. Okay, so there are some alternative ways of looking at the formula for conditional probability. And here's the so-called multiplication way of looking at it. And there's really nothing magic about it. If you look at this formula, we can multiply both sides by the probability of f. This really tells us that the probability of the intersection that E and F occur together is nothing but the product of the probability that F occurs and the probability that E occurs given that F has occurred. And in fact, since the intersection is commutative, we can actually swap the role of E and F, and we get exactly the same thing. The probability that E and F occur together is also equal to the probability that E occurs and the probability that F occurs given that E has occurred before. So E and F can occur together. That's the intersection. Well, if E occurs before, then you can compute the probability of F given that E has occurred. If you multiply the two, you get the probability that they both occur together. Or you can do it the other way around. That's the intuition, but from the point of view of the mathematics, it's just multiplying this equation, both sides of this equation, by the probability of F. The advantage of this multiplication rule, sometimes over the formula that we started with, is that this formula only makes sense if the probability of F is non-zero. Why? Because we can't divide by 0. But you can multiply by 0, so this formula, this version here, actually is can be used even when the probability of E or the probability of F is 0. Why? Because if you look at it, if, say, the probability of F is 0, then F is actually the empty. However, the outcome of the second experiment does not depend on the outcome of the first experiment. Okay, they are so-called independent events. So if two events are independent, then it turns out that the probability of the intersection of E and F is actually the product of the probabilities. That's why the probability of getting head-head is 1/4, because it's 1/2, which is the probability of getting the first head, times 1/2, which is the probability of getting the second head. And the two are independent, so you can multiply the two probabilities. Okay, so let's look at some examples. Well, first let's connect this with the definition of conditional probability. So suppose that E and F are independent. And now remember that this means that the probability, formally, this means that the probability of the intersection of the two is the product of the probabilities of E and F. Now let's see what happens to the probability of E given that somebody tells you that F has occurred. Well, it's a simple calculation. We know that this is equal to the probability of A intersection F divided by the probability of F. But since E and E are independent, we know that the probability of the intersection of the two is the product of the two probabilities. Since E and F are independent, if somebody tells you something about F, it does not affect the probability of E at all, because it's independent of F. That's why the probability that the second coin toss is head does not change if somebody tells you, oh, by the way, the first time I got a head. The two are independent, so the probability is still a half. So that's why if E and F are independent, you don't need the formula for conditional probability to calculate the probability of E given that F has occurred before. The fact that F has occurred before does not give you any extra information that you didn't have before. So the probability of E given F is the same as the probability of E, because F does not change anything. Any doubt about this? For once, probability can be something that makes intuitive sense. There are lots of cases in which it doesn't. So leave all your intuition behind and use the formula to get them right. But let's see what happens. Suppose I tell you, okay, you have a die, you roll it twice. Is the probability of getting a 3 on the first roll independent of the probability of getting a 3 on the second roll? What would you say? Okay, so if you're playing Monopoly, like I have to do quite a bit of these days, okay, I throw a die, I get a 3. I take the die again, I throw a 3. Well, the two are independent events. It doesn't really matter what I got the first time. Shall we see whether the formula is in this case? So let's see. Oops. I was erasing and I didn't mean to. So E now is the event first roll gives 3. F, or, well, actually should be second. So this is F. Well, and E is the event second roll. Gives 3. Okay, so what is the probability of F? It's 1 over 6. The probability of E is the same. So their products is 1 over 36. But what is the probability of E intersection F? Okay, so what is the probability of E intersection F? It's 1 in 36. Why? Because there is only one pair of outcomes, which is first roll is a 3 and second roll is a 3. It's namely you get a 3 and then a 3. It's 1 out of the 36 possibilities that you get by throwing the same die twice. Which is exactly the probability of getting a 3 the first time and the probability of getting a 3 the second time. So the mathematics tells us the same thing that our intuition tells us, namely the two events are independent. Because the probability that they happen together is the product of the probability that they happen independently, one after the other. Okay, so that's all for today. On Thursday, we will be looking a lot more at conditional probability, introducing what I mentioned before, namely Bayes' theorem, which is a theorem that gives you yet another, very often more efficient way, a more useful way of calculating conditional probabilities, which is nothing but a sort of slight variation on the formula that we met today. Okay, if there are no questions, I'll let you go and have lunch in case you didn't have it before.